Okay, good evening, everyone. Let's start with the session. We had been is my screen visible? Can you confirm? Is my screen visible? Am I audible?
Yes, sir.
Okay. This is the problem solving session for basic electronic course NOC 23E62. This is week 5 on March 4th. And my name is Amit. I am a PhD student at ISC Bangalore. So this is the fifth session, as I told, and we have been talking about. We have in the first session we talked about Thevenin and Norton equivalence and how we can switch between them, and then nodal analysis, and we saw a few problems, superposition theorem, and finally phases. Phases are nothing but sinusoidally steady state of representation of currents and voltages. In the second session, we saw problems on RC transients and RL transients, and more importantly, we saw how does the switching impact the transients. That's we saw. In the third session, we saw diode based circuits, that we saw Zener as a voltage regulator, clamper circuits, peak detector circuits, and so on. In the last class at session 4, we saw another circuit of diode, that's a half wave rectifier, and we saw that how if there is also a filtering capacitor present, and how it represents the ripple voltage. And finally, we saw a few problems on the biasing in BJT circuits. So we'll continue with the biasing in BJT circuits, and we'll jump in. But just a quick introduction. What is a resistor? Resistor is a device that when you apply a potential difference with the two terminals, the current will start flowing between them. So in the picture in the center, the potential on the left is equal to potential on the right, hence there is no water flowing. However, if there is a case when the left potential is greater than right potential, then this means the left side is shifted a bit upwards, it's raised, then the water will start to flow from high potential to low potential. And this is the opposite case. When the right potential is higher, then again the water will start flowing from high potential to low potential, that is on the left side. Now the key thing to note is that there is only two terminals here which are determining the flow and direction of the current. However, transistor is a different kind of device. In this, a third terminal it will control the current flowing between other two terminals. So this is the other terminal, these are the two terminals A and B, and this is the third terminal in between. So how much current flows is determined by the third terminal. Here you can see the water level on the left is just above, is such that it is just above the middle level. So what will happen is that very less amount of water will flow to the right side. However, if there is some way which I can lower the barrier, which is in this case, that means a lot of current can flow. Mind you, the water level on the left side is still the same, and the potential between left and right is also the same. It's only the center barrier that we are changing. So if I lower the central barrier, then again the more amount of water will start to flow from left to right. On the other hand, if I lift the barrier such that the water level, the central barrier is now even above the water level of the left, then no current can flow. This is the raising the barrier. So what we are seeing is that even though on the left and right in all these three cases, the potential of left and right is the same, however the current is not same, current is different. In this case, there is even no current flowing. So that means the third terminal, this terminal, the middle terminal, is controlling the flow of current between two other terminals. Junctions, when we talk about in BJT, the case of BJT, when we talk about junction, we mean PN junctions, which is also the case for diodes. Bipolar term denotes that the current is due to both electron as well as holes in BJT. So this is a complete picture. So this we saw in the last slide, and then there are two flavors of BJT. First is the NPN and then the PNP. NPN, we will restrict ourselves to NPN BJT. In NPN BJT, electron is the majority charge carrier while hole is the minority charge carrier. Note, current is due to both electrons and holes. And finally, this is the schematic of both of them. So you have emitter, base, and collector, and you have IC, IE, IB, and IE flowing, and this is the symbol for that. This is the symbol for an NPN BJT. The key thing to note is that arrow is flowing outwards from base. So where the arrow is, that's the emitter in both the cases. But if the arrow is flowing outwards from the vertical branch, that means it's an NPN. If the arrow is flowing inwards, that means it's a PNP. And these are some device characteristics just for the BJT. The width and the doping should be such a manner for an optimal BJT performance. Right. So this is the working of BJT, which I'm showed here on your top left. What you see is an unbiased BJT. So that's why you see Fermi level is constant. However, when we bias in such a manner that this junction, base emitter junction, is forward biased and collector base is reverse biased, a large amount of current will start to flow, which is being shown here. Large amount of electrons will diffuse from emitter to base when it's forward biased. Very few will recombine over here because base is very narrow and low doped, and a lot of them will drift to the collector where it will be collected, and thus the circuit is complete and the current can flow. And these are the expressions, which this is nothing, the first expression nothing but the KCL, Kirchhoff current law. Second is the current gain, and this is the injection efficiency. Right, and this is the complete summary as far as biasing is concerned, DC biasing concerned. This is the slide of utmost importance. So in between A and B, okay, let's talk about between B and C. This is the region which is called the active region. Okay, this is called the active region. So what we have here is that base collector is reverse, my base emitter is forward bias. So we'll be operating between B and C. However, if both are reverse, then we will be operating in the cutoff region, which is the orange region here. And the third region of interest is this linear region or the saturation region, and it's called, in this, base emitter forward bias as well as base collector is forward bias. So both are forward bias in this region, and usually this value that you see here, this value over here, this is usually provided in the problems. So this is also referred to as by the VCE SAT, that is the potential of VCE at which the device enters in saturation. So, and this is the load line, so if this BJT is providing power to some load, so this is the maximum voltage that can be derived is VCC, and while the maximum current that can be derived is VCC over RL. Okay, so that's the theory part. Now while solving the problems, there's a few considerations which is just good to have in your mind. So for an NP and BJT, VB is 0.7 for active and saturation, and for saturation, as I told you, the saturation limit is 0.2 volts for VCE SAT. While solving problems from PNP BJT, it's fairly simple. You just reverse the sign of B and D. So if it's VBE, you write it VEB. If it's VCE, you write VEC. And VT is 26 millivolts at room temperature. Room temperature is nothing but 300 kelvins, or you can say 27 degrees Celsius. And we'll assume that betas are large unless the question says otherwise. So just based on these assumptions, now we'll quickly jump into the problems. So here is the first problem. It says that for the common emitter amplifier shown in the figure, assume that BJT is operating in active mode. What is IC? So this is an amplifier. Why it's amplifier, we'll see. It's fairly clear because you see IC is beta IB, and beta is usually very large, so you're getting large amount of current if you provide a small amount of input current, right? So now it's saying that it's in active mode, so that's given, and say it's a common emitter amplifier. What does this term common emitter mean? It means that this emitter is common to input side as well as output side. So you see this part, the left part is the input side, while the right part is the output side, and emitter is the terminal that is common to both of them. So emitter is present in the left side as well as in the right side. Hence this is emitter is common to both input and output, and hence this configuration is also known as the common emitter configuration. So this is the problem given. We are given that BJT is in active mode, and we are required to find what is the collector current IC. So let's mark the current here as well as the required node voltage which we require over here. Now the key thing to note here is that since we are talking about only the DC analysis, so what we'll do is that we'll just drop all these capacitors. So why is it safe to drop them? So because inherent assumption is that these capacitances are large. Right, and and in the DC analysis, so you can see that Z equal to 1 upon omega C, right? So if it's 1 upon omega C, if effectively you're saying effectively what we are saying is that omega is such that these capacitance will not play a role. So in the DC analysis, we only consider the inner portion, so to speak. Okay, so that's the key thing to note over here. So let's now go ahead and do this. So if we talk about the DC analysis, as I told, I've already marked the node voltages, right? So now what I'm going to do now, let's do, okay, So how should we proceed with this? Is that right? So what we'll do is that I'll apply, first of all I'll see that what is this node voltage VE. Let's try to evaluate what is the node voltage VE. So node voltage VE can be simply written as, if I apply Ohm's law across this resistor, it can simply be written as IE times 3.3k. That's nothing but that's the voltage VE. Now if we know VE and we also know that this is operating in active mode, then what we can do, we can obtain VB. How? Because we know VBE is 0.7. This means VB minus VE, this should be equal to 0.7, and we already know the value of VE, so we can get VB, this should be equal to this VB now will come out to be VE plus 0.7, that is 0.7 plus IE times 3.3k. Now we are required to find VB. So how do we find that? So we are going to find that by using the information that so there is a current flowing through this loop also, right? And this is nothing the potential divider. So VB is nothing but the voltage of this potential divider. Okay, so we'll find VB using potential divider. So how do we do that? We can simply write that VB. Now note that we are ignoring the very small amount of quantity of current that will be going through here, right? There will be some current flowing through here, but usually we'll see that if we can ignore it. But for now we are ignoring the IB that's flowing through here. So we are assuming all the current is flowing, like from I1 is equal to approximately equal to I2. So let's do that. So VB I can write then, this VB will be 12 over 20 plus 15k times 15k. Okay, let me get my calculator. So it will be 12 times 15 over 35. This is coming out to be 5.14 volts. If VB is known, what I can do is I can find IE from this. Okay, now step 4 is what we'll do, find IE. So find IE. So if we do that, this will give us IE is equal to, so that will be 5.14 minus 0.7 over 3.3k. okay, so let's do that, minus 0.7, so that's coming out to be 4.44 over 3.3k. this value comes out to be around 1.34 milliamps. So the expression, the value for IE is coming out to be around 1.3, it's 35, sorry, it's 1.35 milliamps. Now since we'll assume that beta is large, so we can say that this implies that IC is approximately equal to IE, which is again 1.35 milliamps. So that's what we do, and we see if there is a close by option 1.34. yeah, so option B is there, and this is a fairly close call, because remember that we have ignored that some current is flowing through here. So and these options are far apart, so with reasonable degree of confidence we can say that the B is the correct option. So that's how we did it to finding the current B, and usually this is the most important step in the DC biasing of a transistor, because this will determine that how ultimately the small signal performance of a BJT, how it looks like. So this is an important part, and we just arrived it just by using the DC analysis. So the correct answer is 1.3 milliamps. Now let's quickly jump to the second question. In this says that for the amplifier of Q1, the value of RC is required to obtain VC equal to 5 volts. Okay, so now what we are given, we are also given VC equal to 5 volts. Okay, so so what we are doing, okay, so this is wrong, this is not 0.8, this is actually 1.3, right? It was 1.3, yeah, so it was 1.3. So now, and these are the currents and the corresponding voltages. Now how do we find RC? So it's straightforward. What I'll do is that I'll choose a different color. What we'll do is that, so we'll apply KVL along green line. We'll apply KVL along green line. So let's do that. So it will be 12 minus ICRC minus VCE, this drop, minus IERE equal to 0. Again, I'll assume since beta is large enough, so I'll say that IE is approximately equal to IC, which is equal to 1.3 milliamps. So let's put this value over here. So what we'll get is everything is known except for the RC term. So I'll keep ICRC here. This will be 12 minus VCE minus IERE. So this will come out. This will come out to be 7 minus IE is 1.3 milliamps times 3.3K. This will also be 1.3 milliamps times RC. This will give me RC equal to 7 over 1.3 milli minus 3.3K. So this turns out to be 7 over 1.3 milli, 7 over 1.3 comes out to be 5.39 kilo minus 3.3 kilo. This will come out to be 2.1 K. So it's coming out to be around 2.1 K. So let's see, do we have an option around 2.1 K? Yeah. So we have C. Now again you will see that it's close. Why is this certain discrepancy? Is because remember that I assumed I equal to IC. So if we do the actual proper calculation, so what you can see, the I value will be slightly higher. So this value corresponding will be again be slightly higher, and hence you'll get closer to 2.0 K. So but this is the option that matches, so we can go ahead. It's not a problem. So we can go ahead with this. So now we have found out actually two important points. So first, remember in the first question we identified what is the value of IC. We have seen that IC was coming out to be 1.3 milliamps, right? And now we have found out for VCE equal to 5 volts. Now this is what is often known as the Q point, quiescent point, or the DC bias point. There are different names of calling it, but this is the point that's of utmost importance, because in order to obtain small signal characteristics, we must first of all have the DC analysis, and the result for DC analysis that we have is that this is the result that we are getting. Okay, so now let's so I'll pause here for a bit because we have completed the DC analysis, and I'll ask 1 second. Yeah, I'll pause here for a bit, and if there are any comments or questions till now, you can ask. So just to reiterate, we had till now we have calculated the value of IC, and if we persist with this value, then the value of VCE also, and this is collectively this is often known as the Q point or the DC bias point of the circuit. Okay, so now let's move forward. 1 second. Okay, so now moving forward, what we have is now the problem says with RC set to the value obtained in Q2. So remember that we had obtained for the value of RC, but this is the Q point, that quiescent point that we had obtained, right? So it says that for the value of RC, so RC was 2K if you remember, IC is 1.3. We are required to find the GM. GM is also known as the transconductance. Somebody is unmuted. Can you please mute yourself? Sneha, can you mute yourself? Please mute yourself. Okay, so what we are required to find is the GM, which is the transconductance. Now how do you define GM? GM is defined as the derivative of collector current with respect to the voltage of base emitter voltage. So the collector current is often written as some constant I naught e to the power VBE over VT over dVBE. So this is the independent variable VBE. So if you differentiate it, it will come out to be I naught by VT e to the power VBE, because exponent of VT, exponent of x will just replicate, and the internal term will give 1 by VT. No, now note the numerator is nothing but IC again, I naught e to the power VBE over KT. So GM is written as, the expression for GM comes out to be GM equal to IC over VT. And so now we know IC, which is 1.3 milliamps. We know VT I told you, if nothing is given, we'll assume the room temperature, and the value VT comes out to be 26 millivolts. So if we solve it, this is 1.3 by 26, that's 1 over 20. The units is the inverse of ohm, that is mho, or also sometimes also written as Siemens. So that's coming out to be 1.1 over 20. So 1 over 20. Okay, so 1 over 20 is nothing but 50. So 1 over 20, that is mho, which is also equal to, if you convert it into milli, so that will be 1000 by 20 millimho. This will be 50. So the numerical value of GM, by the way, the expression again I repeat was IC over VT, is coming out to be 50 millimho. And again, as I again reiterate that we know already the bias points, that is, we already know the IC and VC, then only we can jump into the small signal analysis. So that part you must always keep in the back of your mind, because that is the that's how we are approaching these problems, all of these problems. First the DC analysis, and then once we are finished with the DC analysis, then only we can go forward for the small signal analysis, right? So this question is done. Okay, so now let's jump to the fourth question. So what is it? It talks about it for the value of RC set to obtain in question 2. Again, it refers to question 2 over and over again, because we had fixed the question point in question 2, which was IC equal to 1.3 milliamps and VCE equal to 5 volts, and this happened when RC was 2K. So that's why we keep on referring to Q2 always. So the value of RC is set to obtained in Q2. What is R pi? So R pi is so essentially GM, R pi, these are which we see ultimately we are building up for this small signal model of a BJT, and we'll see that how do these terms come into picture. But for now, let's just calculate the numerical values for the. So this is the values that are given to us. We are required to find R pi, and these are the currents, though they are not relevant for this problem. The expression for R pi is nothing but beta over GM. It's beta over GM. So let me just introduce the circuit for now, that what R pi are we talking about. So this is the R pi. This is your base. This is your emitter. And this is your, so this is GM, VBE. GM is the transconductance, VBE is the voltage that we read across the resistor R pi. This is also known as, by the way, the pi model. Okay. So R pi, we already obtained the GM. So it's beta over GM. So value of beta is 120. The value of GM, if I remember correctly, was 50 micromho. So this will come out to be 2.4 over this will be milli, this will be K. So sorry, 1 second, my bad. So this will be 2.4 over 50, that's 2.4 over m ohms. So it will be 2.4 kilo ohms. The value of R pi will come out to be 2.4 kilo ohms. Yeah. So let's see, is there an option? Yeah, there's an option exactly matching, which is P. So fourth option is P. As I told you, so we are obtaining GM, R pi. These are all how should I say this? These are all the different terms that we come across in our small signal model. So GM and R pi, and we saw that this is how the small signal, this is the collector, right? So in the common emitter configuration, this is how the small signal equivalent of a BJT looks like, right? So now we have obtained R pi. Now So now for the time being, now we'll switch back, we'll again go back to the DC analysis. So the question says that with RC set to value obtained in Q2, now suppose R2 is varied. So we fixed the RC and now we are varying the R2. At what value of R2 will the BJT just enter saturation? Okay, so that's the problem. This means, so R2, so RC is fixed, if you remember it was 2K. And if we also remember that corresponding to this VCE was 5 volts and we are operating in active mode, active region, right? So now the problem asks is that now if we change the value of R2, its mode might change, so it might may go from active to cut off or from active to saturation. So in this case it's asking that when does it enter saturation. Now just in order to define saturation, if you recall that for that VBE must be forward bias, so that means it should be 0.7 volts, and VCE sat should be equal to 0.2 volts. This is the assumptions, if you recall, that we had seen that these are the values that we are supposed to follow. Okay, so so we know that RC is 2K, right, and we require R2 for entering saturation. That means we can say that VCE should be equal to 0.2. We are just interested in the boundary condition, at what value of R2 will we enter the saturation. Okay, and these are the corresponding currents that we have, and these are the node voltages. Now as before, so RC is fixed, RE is fixed, so what, and VCE also fixed. So effectively everything in this I'll denote with different color. Everything in this green path is known to us, right? So as a step 1, what we'll do, we'll apply KVL along green line. So let's apply KVL along green line. It will be 12 minus ICRC minus VC, that is a drop over here, minus IERE should be equal to 0. So so I'll take all the terms again. I'll assume, since beta is large enough, I'll assume IC equal to IE. This is an assumption, right? So then I can write that it will be IC times RC plus RE should be equal to 12 minus VCE. This is 12 minus 0.2. So this will give me IC equal to 11.8 over the value of RC is 2K plus 3.3K. This comes out to be 11.8 over 5.3K. So let's see what this value comes out to be. 11.8 over 5.3. This is coming out to be 2.23 milliamps. So the value of IC, that is just when you are entering the saturation, is 2.23 milliamps for the given values of RC and whatnot. Now, but we are required to find what is the value of R2, right? So now in order to find the value of R2, let's just find what is the value of VE here, right? Because if we find VE, then we can find VB, because this is again forward bias, and if we find VB, then we can evaluate the currents that are flowing over here. So as a step 2, what we'll do, this is step 2, so we'll find VE. So how do we find VE? VE can be found just by applying Ohm's law across this resistor. So that will be nothing but IE times RE. Again I'll assume IE equal to IC, so this is 2.23 times 3.3K. so this value will turn out to be times 2.23 times 3.3. this is coming out to be, sorry, I made a mistake, 2.23 times 3.3, this is coming out to be 7.36 volts. So this is actually 2.23 milli. So milli and K will get cancelled. So we got VE equal to 7.36, and thus I can get VB should be equal to, because VB is 0.7, right? So VB minus VE, let me write it again. So VB minus VE should be 0.7. This will give me VB equal to 7.36 plus 0.7, which will be 8.06 volts. So now I obtained VB as 8.06 volts. Okay, that's good. Now what I'll do is that now I'll apply KCL at VB node. Okay, so as a step 3, let me do on the next slide. So as for step 3, we'll apply KCL at VB. So what was VB? This was VB, and this is the current I1, this is the current I2, and this is the current IB. So incoming current should be equal to outgoing current. So incoming current is nothing but I1, outgoing current is nothing but IB plus I2. What's the value of I1? I1 can be obtained if we apply Ohm's law across the R1 resistor, right? So let's do that. So it will be 12 minus VB over R1. This should be equal to IB plus the value of I2 is nothing but VB, that is Ohm's law across R2, VB minus 0 over R2. Okay, VB we already know, that's 8.06 volts. So let's put this value here. So that will come out to be 12 minus 8.06 divided by the value of R1 is 20k. This is coming out to be 0.197 milli. The value of IB is nothing but IC by beta, right? And this is nothing but the value of VB is 8.06 over R2. So let's take 8.06 over R2 to one side. This will come out to be 0.197 milli minus the value of IC was the value of IC was 2.23. So 2.23 milli divided by the value of beta is 120. Okay, so 2.23 divided by 120, this will come out to be 0.019. okay, so if I subtract this from 0.197, sorry, 1 second, plus 0.19 minus 0.197, this come out to be minus 0.178. so it's come 8.06 over R2. This is coming out to be minus plus 0.178 milli. So this will give me, write it here, R2 is 8.06 divided by 0.178 milli. So let's get this 8.06 over this number. It's coming out to be 45.2 kilo ohms. So we'll round it off and let's say 45 kilo ohms. So which is the option? So there is no option. Actually what I feel is that this decimal is a misprint. So we'll just say that this option is nothing but 45, and let's say A is our correct option. The numerical value is important. It's coming out to be 45 kilo ohms. So this was problem 5. Yeah, the answer sheet says it should be A, but there's a clearly the decimal is misplaced over there. So what I'll do is I'll quickly go through this, summarize this problem once again. So what we have is that, so we know RC, now we are required that we will now vary R2, and we'll need to find that when it just enters saturation. So just entering the saturation, VB should remain forward bias, that is 0.7 volts drop, while VCE should be equal to VCE sat, that is 0.2. So using this information, I apply KVL along the green line, which is this curve, and I find the value of IC, which comes out to be 2.23 milliamps. Finally, once I know IC, I can find VE, right, which comes out to be 7.36, and then since VB is 0.7, I can find VB, and once I know VB, now if I apply the KCL at this node, so again I reiterate that the AC part we are ignoring completely. Okay, so and then we apply the KCL at VB, and we finally evaluate the R2 value. The value of R2 is coming out to be 45 kilo ohms. So that completes the problem. At this value, the BJT will just enter the saturation mode. Mind you, it was operating in the active prior to in Q2 question 2, it was in active mode, if you recall, because VCE was 5 volts and VB again was 0.7 volts. So that's how we do this. Now as we had talked about, that there are the three modes that we see of the three typical modes that we see active, we see saturation, and we see cutoff, right? So we saw we were in active mode, which is in question 2. Saturation we saw in question 5. Now cutoff we'll see in question 6. So it asks that again RC is set to question 2, which is RC is again 2K, this means, And finally, and R2 is varied, so this is the resistance which we are again varying, so this will not be 15k. We are required to find the value of R2 at which this BJT will just enter the cutoff mode. Okay, so how do we define the cutoff? We define the cutoff when VBE drops below 0.7 volts. Okay, when VBE drops below 0.7 volts, that's when we defined as the cutoff. Or an alternate way of you can saying is that since this is no more forward bias, so there are two different versions that that we can talk about. Let's proceed and let's see which suits better for our approach. Okay, so as RC is 2k, we are required to find R2 for entering cutoff, and these are your corresponding voltages and currents. So so what we do is that since RC is 2k and okay, so we are required to find the voltage at which we are entering the cutoff. What this means is that, right, so I should write it this way. Cutoff implies that IC is approximately 0. This means it will not be 0, there will be, because there will always be some leakage current that's flowing, but for all practical purposes we will say that IC is 0 milliamps. Okay, this means there's no current flowing through this loop completely at all, because it's cut off. If you remember the earlier slides which I showed you, these were different curves, and just at the very bottom, just at this region, the orange portion region, so this current you see, this was IC versus VCE, and so this current is very low, so we'll assume it that the current is 0 milliamps. Okay, over here. Okay, so there is no current that is flowing through here now. So what that would entail is that so VE is essentially 0, right? And if no current is flowing over there, then I can also say that IB is also 0, because remember that we are just about to enter the cutoff. Okay, so these will so beta equal to IC upon IB. This holds true when we are in active mode, right? At least when you are in active mode, and we are operating in active mode, and then we are entering cutoff. So we are about to enter the cutoff, and this expression will again hold true. So now what's going to happen is that all the current the currents that we talk about is that will only be flowing in this loop, in you see where I1 and I2 is flowing, right? So what I'll try to do is that, so using the potential divider, we try to find what is the value of VB. Okay, so let's try and do that. Oh, sorry. Yeah, so let's try and do that. We try to find the value of VB. Since no current is flowing here, this is a pure potential divider, and I can simply say that VB is equal to 12 times R2 over R1 plus R2, right? So this is the expression for VB, and we know that for cutoff, when do we enter cutoff? When I told you, when VBE drops below 0.7 volts, right? So let's use this expression. So let me erase this for now, right? And so we'll write VBE is less than 0.7 volts. That means VB minus VE is less than 0.7 volts, and if you recall, VE is 0 because there's no current flowing through here. So this node will also have 0 potential. So I can simply say the expression for VB is this. So it will be 12 times R2 over R1 plus R2 should be less than 0.7. Okay, so now let's just rearrange the terms. So it will be 12 over 0.7, which is coming out to be 17.15. This can be write as 17.15 should be less than R1 plus R2 over R2. I have just cross multiplied the terms. So let's go to the next slide. 17.15 should be less than R1 plus R2 upon R2. Let's divide by R2. So it will be 17.15 should be less than R1 over R2 plus 1. This should give us R1 over R2 should be greater than 16.15, and thus R2 should be less than R1 times 16.15. Let's put the value of R1. This less than sign is coming because just since we are interested only in the equality, right? So we can drop this, we can even put this equal to, but I'm just to emphasize that if we find the range of R2s, then we'll be fine. So R1 value is 20k over 16.15. so 20 over 16.15 comes out to be 1.24. so this is coming out to be 1.24 kilo ohms. So since we are this word is important, just this means we can drop the inequality and replace it with an equality sign. So R2 should be equal to 1.24 kilo ohms, and thus the closest option that we get is option D. So this will be our answer, and let me check the answer key. Yeah, it is indeed option D. So how did we do it? Let me summarize it again. Since we are required to find the value of R2 when we are just about to enter cutoff, so we first analyze what does cutoff even mean. So cutoff means when IC is 0, IB is 0, the transistor is just not working at all. All the currents are 0. If all the currents are 0, what this would mean is that VE will also be 0 because there is no potential drop here, and also additionally VC will also be equal to 12 volts because again there is no potential drop here, right? So this is the first piece of information that we have. Secondly, we need to find VB. How do we find VB? Since no current is flowing here, this is a pure potential divider, the circuit between the 12 volts, R1, R2 and ground. So using the potential divider expression, we can write VB equal to 12 times 12 is the, by the way, the voltage, times R2 over R1 plus R2. And we know that since we are entering cutoff, so that means VB should be less than 0.7 volts. VE is 0, which we know here, and so VB should be so thus putting all the terms here, then that is nothing but the algebra. So we finally arrive that R2 should be less than 1.24 kilo ohms. Less than comes because we are covering all the range for cutoff, and for just entering the cutoff, the answer should be 1.24 kilo ohms, and the closest option that we have is 1.2 kilo ohms. Hence D will be our answer. So that's that. Since we are again jumping into the small signal analysis, I'll wait here for a minute or two. If you have any doubts, you can ask. Okay, so if 1 second. Okay, so if there are no comments, then we'll just move forward to the next problem that we have in the same set. So it says that with RC set to the value obtained in Q2. So again, remember Q2 was our bias point where we obtained VCE as 5 volts, and I forgot what was the IC. I think it was 1.3 milliamps. This was the quiescent point that we had obtained, right? So what we are required to find is that what is the mid-band gain V0 over Vs. Okay, so we'll see what Vs is denoted here and V0 is denoted over here. So we are required to find what is the, if RL is large. So there are a few assumptions that we are making here. So first we need to see what does this term mid-band even mean, right? So the relevance of this term, how should I say this? Okay, so usually band means a range of frequencies, right? This means a range of frequencies. So what we want is that so let's just try to evaluate and for every frequency, if you remember that there's an impedance associated with every capacitance, so which is 1 over omega c. I'm just writing the magnitude over here, okay? So there'll be a j also, but let's drop that. Let's just talk about the magnitudes first. So z equal to 1 upon omega c. So let's say when omega is very large, right? For large omega, Z, when the omega is large, Z will tend to 0. Okay, this means short circuit. Okay, and when for small omega, Z will tend to, also Z will also depend on C by the way, but here I am assuming, if we assume a moderate capacitance value, Z will tend to infinity. That means an open circuit, right? And you can do the same analysis for a C, but we are talking about midband omega. So how does the midband omega, how does it behave? Then midband omega will depend exclusively on the values of C, because just by the value of omega we cannot short circuit or open circuit this capacitance, right? So for mid omega, what we do is we look at the capacitance. For mid omega, again for large capacitance, so I'll write this midband omega and large capacitance, what we'll have, this value will again be large, right? So again Z will tend to 0. This means a short circuit. This means there's no impedance that it's seeing. Similarly for midband omega but small capacitance, what's going to happen is Z will tend to infinity, because this term will blow up, this, which we can denote it as the open circuit, right? So this is the takeaway from this, the bottom two rows. So because we only interested in mid omega, so this is the thing. Now the question that opens up is, what are the values of CB, CC and CE, because then only we can determine whether it's short or open. So the typical values that we use for this CB, CC and CE, they are large, right? So let me write that assumption on the next slide. So we know, since CC, CE, CB are large, they behave as short circuit. Okay, so that's the first thing. Second thing, we know in AC analysis implies that deactivate independent voltage or current sources. So we deactivate all the independent voltage and current sources when we are talking about the AC analysis. So taking these two informations, let's redraw the circuit. Okay, let's redraw this very circuit. So what will happen? Vs will remain the same. Vs will remain as it is. Now CB is shorted, so I'm just replacing with a wire. So that's this wire, right? So this will be R1. R1 is connected to ground. This is an independent voltage source. This will be ground. R2 is connected to ground. So this is R2. This is connected to ground. This is R2. Then we have is nothing but your BJT. So let's keep the BJT as it is for now. I'll again replace it with small signal model in a minute. So, and this is connected to RC, which is again connected to a ground. This is RC, right? And CC is again shorted. We assumed it to be large, right? And this is RL, okay? And then we have this RE, and we have, since CE shorted, so this is a short like this. This is the complete circuit diagram. I'm still not replaced the BJT with its equivalent model, right? But even now you can clearly see that. So first you can see is that R1 and R2 are in parallel because both are connected to the ground, and R1 and R2 are parallel, right? So, and also now in the next step what I'll do, I'll incorporate the BJT small signal model over here. So let's do that. So this will be Vs, okay, and what I'll do, I'll bring R1 down just like this, just like its counterpart R2. This will be R2. This is ground, okay. And we know we can replace the BJT with its equivalent model, which looks something like this. R pi, excuse me, Yeah, okay, one more thing. RE gets eliminated because RE, and this is zero resistance path, and this is RE. So RE will get dropped out. Okay, so this is the equivalent circuit model like this. This is your base, this is your emitter. So you can see emitter is connected to ground now by this wire. So this is that wire I'm denoting here. And finally the third terminal which we have is the collector, which is connected by a current source over here. And here we have, this is the collector, and we know from the collector there is a, this is RC. Note, RC is connected between collector and ground. So between collector and ground, and finally this is RC, and again this is your RL. So this is your complete circuit diagram of this AC equivalent circuit diagram for this, right? So I'll just I'll revisit this because this is important how we arrived here. So first we since assuming that CE, CC and CB are large, they'll behave as a short circuit because 1 upon omega C. Okay, so what I did was that I dropped CB, I dropped CC. So CB was dropped, you see a short here. CC was dropped, that's why you see a short here. There's nothing in series with RL. Finally CE, that's why you see a wire here. Okay, and finally we deactivate independent voltage source. So 12 volts was replaced by a ground. This was the circuit. Now R1, then I just rearrange these circuit elements. So R1 and R2 are in parallel, which we can see over here. And finally I replace this BJT by its small signal equivalent, which is over here. And RC and RL, RC is connected to collector and ground, RL again is connected between collector and ground, and hence they are also in parallel. Okay, so what I'll do on the next slide, I'll redraw this diagram. Okay, so let's redraw that diagram. So that was something like this. Vs, R1, R2, R pi, and then we have, this is the emitter, and then we have this is nothing but GM VBE. I forgot to write in the last slide. So the value for this is GM VBE. What is VBE? This voltage is VBE. Okay, so and then there is a RC, and finally there is a RL, and this is the output voltage V out across RL, right? And this is again ground. Now again since this was mid-band, I again made some assumptions that the hybrid model looks something like this. Otherwise, if this were not there, then it will add two more capacitances, right, which I'll show and then I'll delete. So what happens is that if this model were not true, right, there will be a capacitance here also. This arises due to the how BJT is fabricated, and also there is one capacitor over here, right? So over here something like this. But since this capacitor are very small values, these purple capacitors are very small values, and we saw that for small capacitors it's an open circuit, right? Since these are small capacitors, we'll assume them to be open circuit, and hence there's no current flowing, so they are of so they are of no relative prominence to us, hence we did not draw them. Okay, but they are there. Since we're interested in mid band, these will not play a role because these are small. All right, so let's just remove them and just keep our analysis simpler, because otherwise it may get overwhelming. Okay, so what is VBE? This voltage is VBE. VBE. Now you can clearly see, now whatever current is flowing in this circuit and this circuit are completely decoupled from each other, except there is a relation of VBE over here, but whatever current is flowing will keep flowing only in this circuit. You can apply KCL over here. So for instance, so equivalent circuit would be Vs in parallel with the resistor, so no current can flow here. Similarly, no current can flow here. This is only just common ground, but no current can flow between each other. Okay, so what's going to happen is that now we can clearly see that VBE is nothing but Vs. Why? Because both have the VBE, the negative terminal is this, Vs negative terminal is this, and this is a wire. So VBE is equal to Vs. That's the first piece of information. VBE equal to Vs. Now let's just talk about what is V0. So V0 is, so we can see that let's call this current IC for simplicity. Okay, so we can say V0 is nothing but IC times minus IC times, because the current will flow in this direction, RC parallel RL. Okay, V0 equal to minus IC RC parallel RL. So let's try to solve this first, and note that RL is very large, so it will get dropped out. So you can assume this is an open circuit, right? So we'll get V0 equal to minus IC times RC. Again, why IC sign? Because the current will flow in this direction, and the polarity of voltage that we are measuring is this, hence the negative sign. So what's the value of IC? IC is nothing but GM VBE times RC. There's a negative sign here, so I can write V0 equal to minus GM. The value of VB is nothing but VS times RC. This will give me, just a second, okay, this will give me V0 over Vs equal to minus GM RC. So this is the expression that we have obtained for this problem. V0 over Vs, this is what we are required to find. This is called the gain. Why gain? Because it's output voltage, which is V0, over input voltage, which was Vs, and this is also known as the voltage gain. Voltage gain. This is coming out to be minus GM times RC, and this is your expression, by the way. Okay, but a few assumptions. This is mid band, first of all. Second of all, RL is large. So those two assumptions you must keep into your mind. So now what we need a number, so let's put, that's just the easy part. So the value of GM, what was the value of GM? I forget. I think it's also denoted, by the way, by I think AL or AOL, A open loop. Let's just, I'll draw it with a symbol which is easier to, AV is so minus GM, I think this was minus 50 mho times RC, if I recall, was 2K. Okay, so if I multiply it, this will come out to be minus 100. AV is come out to negative sign denotes a polarity is reversed. So what this means is that if your input is like this is your Vs, your V out will be 180 degree out of phase. It will be like this, but 100 times magnified. Okay, let me draw it again. So what this means is that if this is your V in, your Vs, right, and this is your V out, so it will be 180 degree out of phase. This means when it's going up, it will be a down cycle, but 100 times magnified, something like this. This is V0. Okay, but the magnitude is 100. So if this value is, let's say 1 millivolts, this value would be 100 millivolts. Okay, this is the AC component of the value that we see. That's why I denoted in small letters, V0, small v. And remember, when DC biases we were talking about, they were all capital VE, capital VE, capital VB, capital VC, and so on. So but here it's all AC analysis, it's all small letters. So what we obtained was that value was 100, so which is option D that you see over here. So I'll again summarize this because this is important. So what we knew was that we were required to find the voltage gain. We are required to find this mid-band gain, V0 over Vs, which is also known as the voltage gain. Okay, so and then we saw that what do we mean by mid-band, and we came by this analysis that in mid-band, if there is large capacitor, we can replace it with a short circuit, while for small capacitor we can replace it with an open circuit. So and then we saw that CE, CC, CB, we assumed them to be large, and hence we shorted them. And in these AC analysis, we deactivate the independent voltage source, which is 12 volts here. We did all that analysis, we drew this diagram, we simplified it, and we came to this conclusion that this should be the equivalent circuit. Just a second. Yeah, this should be the equivalent circuit, And finally, then we saw that VBE is nothing but Vs, and we also saw that these two signals, these two left and right, are completely independent, current wise are independent of each other. So whatever current is flowing, all the current will flow in this direction, and all the current that's coming will go in this direction. Nothing will, there'll be no crossovers. Okay, so and then we simply just then the rest is just algebra. And we also dropped RL because RL is very large, which is given in the problem, and we obtained the voltage gain to be minus GMRC. We put in the values, which comes out to be minus 100. Minus sign denotes, as I told you, the polarity of output voltage is reversed as compared to the input voltage, hence the negative sign, but the magnitude of gain is 100, which we obtained over here, and hence the correct option would be D. So that's the okay. So there's still some problems remaining from this part. All right, sorry about that. Just a second. Yeah, I hope the screen is visible. Okay, so now what we are required to do, the screen is visible, right? The presentation. Please respond. Okay, I'll just assume that the screen is visible. From my side it is, so let's just go ahead. So now again, in the next problem, it again talks about midband gain. So remember, in the last problem we have already created an equivalent circuit for this, and again talks about V0 over Vs, only the magnitude, right? But this time RL is 2K. If we draw this diagram again, and if you recall what we had done, finally we had arrived to this diagram. Vs, R1, R2, R pi, which is connected to Vs, R1, R2 and R pi. These are the on the input side, right? And they are all connected to a reference voltage, and on the output side we had this voltage dependent current source whose magnitude was GMVBE, where this voltage is VBE, and then we had RC, and then we had RL, and we are taking the output from this. So this is the input, and we saw that output, the expression for midband gain was coming out to be minus GM RC parallel RL. This was the expression that we had derived. Okay, so now let's just there's nothing to do, just to plug the values. So this will be minus GM 2K parallel 2K. This will be minus GM is minus 50 millimho times 2K parallel 2K is 1K. So 1K and milli gets cancelled. This will comes out to be minus 50. So we again see that AV is coming out to be minus 50. And as I told you, the importance of rather the negative sign, it's that the output voltage is 180 degree out of phase with the input voltage. That means when input voltage is rising, when the input voltage has positive half cycle, the output voltage has the negative half cycle, and the magnitude is, in this case, is 50. So we are required to find the magnitude. So we can clearly see that mod AV, which is 50, this sign magnitude. So mod AV is coming out to be 50, which happens to be option B that we have over here. Right, this is just an extension of the previous problem, nothing new to add. So hence now we'll quickly jump to the so let me just do one thing, just a minute, so that let's save some time. Okay, I don't think that will be possible. Okay, so now let's just go to problem 9, which says that with RC set to a value obtained in Q2, this is again the question point which I'm emphasizing again and again. VC equal to 5 volts, IC equal to 1.3 volts. To AC analysis, you must have some question point fixed. That's what the question 2 denotes. What is the output resistance of the amplifier as seen from RL? Now, so what I'll do is that I'll draw the diagram again. Okay, this is Vs, R1, R2, this was R pi. Okay, and this side we had GM VBE, RC, and here we had RL. This is our output voltage V0, and this was our VBE, this voltage, this. Okay, and this was our reference. Now it says that what is the output impedance as seen from RL. So this means we are required to find what is the impedance that we are seeing when we look from over here. Okay, when we look from over here, what kind of impedance do we see? So what essentially this problem is saying is that you want to find the Thevenin equivalent of the, I'll draw what diagram we are talking about. You want to find the Thevenin equivalent resistance of this purple block, because we are looking from RL. So from RL, this is the external part, and we are required to find the Thevenin equivalent. Okay, so we are required to find, so R0 will be nothing but RTH of purple block, right? And how do we find R Thevenin? If you recall, the way we find R Thevenin is you deactivate all the independent sources. So first let's draw the purple block alone. Vs, R1, R2, R pi, and then we'll have GM VBE and RC, right? And we're required to find the Thevenin equivalent from looking from here, right? And we know when you find Thevenin equivalent, you short circuit all the independent voltage source. So this is an independent voltage source, right? This is the independent AC input voltage that we are providing. This means that to find RTH, Vs must be made equal to 0. If we make Vs equal to 0, then that would mean that this is VBE. So this would mean VBE would be 0. This means there's no current flowing here, right? So how will the circuit diagram will look like? How? These are shorted, so all of them are gone. This is open, this is also gone. What remains is nothing but RC. You see, if this is shorted, R1, R2 and R pi are all gone because they are just across a short. So this is all of them will be at 0 volts, right? This part of the circuit goes out of the window. Also VBE will become equal to 0. If VBE becomes equal to 0, this means this current source, this voltage dependent current source, will have the magnitude of 0. This means there's no current flowing through this branch, and thus we can open circuit this. So what will the circuit remain? Only the RC component remains in this circuit, and hence we can clearly see that. Because the circuit diagram will look something only like this. This is RC, right? And we are required to find the output impedance looking through this. So we'll find that R0 will be nothing but equal to RC, which is, I believe, was 2 kilo ohms. So 9th will have option B. Yeah, option B is the correct one. So I'll again tell you, because this is a fairly common problem where we're required to find the equivalent input and output resistances of any circuit. So for here we just drew this the small signal equivalent, which we saw in the previous two problems also. We are required to find the output impedance as looking through RL. So whatever is the component that's left of RL, which we denote in this purple block, we need to find the RTH for this, and then we'll be fine. Now to find RTH, we put independent sources to 0. This is an independent source. I'll write this. Independent source. We deactivate all the independent voltage and current sources. This is an independent source. This is not independent. This depends on VBE. So we cannot deactivate this. We have to deactivate only this. But if we deactivate this, R1, R2, R pi are all gone. VBE becomes 0. And if VBE becomes 0, then this also becomes, this magnitude of this dependent current source also becomes 0, and thus this also, 0 current means open circuit, so this will become open circuit, and this is the only circuit element that remains, which we see over here. And hence if you try to find Thevenin equivalent, which will be nothing but RC, the value of RC is 2 kilo ohms, and that is the option B over here. Okay, so that is how we approach these kinds of problems, where we find output resistance of amplifier, input resistance, etc. Similar problem is that now in this case we are required to find the input resistance, right? And it says that from where to look. So we are looking now from this side. Okay, we are looking into the circuit from this side, and we try to find what is the input impedance for this. How will we do this? The same way as we did the last problem. So we'll draw the circuit diagram first, the small signal equivalent. This is Vs, R1, R2, R pi. This was the reference node, if you recall. This is the dependent current source, and here we have RC, and we have one RL. Okay, and we are required to look from this side. Okay, and the problem asks us to find the input impedance when we are looking from this side. Okay, and so this is the voltage VBE, right? So how do we do that? So it's again simple. So again I'll draw the block that we drew from last time, right? So we are required to find Thevenin equivalent resistance for this block. So Rn will be nothing but RTH of purple block. Okay, so inside the purple block, let me first draw the purple block again. Okay, so this will be R1, R2, R pi, this will be GM, VBE. Oh wait, what just happened? Okay, sorry about that. This will be RC, and this will be RL. So as we have been seeing, the left and right part of the circuit do not talk to each other at all, right? So and this is VBE. Okay, so this is the VBE. Now what can happen is that since no current will flow in this part of the circuit, right, there's no current flowing because there's no voltage source. That is, earlier there was a voltage source here which was feeding this circuit, and this current source was feeding these two resistors, but now there is no voltage source feeding them, so VBE will naturally come out to be 0, right? And thus the input impedance that we look from this side, right, we are looking from this side, right? So what we will see is that since VB is 0, this part goes out, this becomes an open circuit, right? And thus no current can flow in this part of the circuit again, because then there's no current source. Here there's no voltage source, now here also there's no current source, right? So what's going to happen is that what we'll have is R2, R1 and R pi. This will be nothing but your Rn, or sorry, small rn. Okay, so what I'll do is that we'll say Rn equal to R1 parallel R2 parallel R pi. Okay, so R1 is 20k, R2 is 15k, R pi we have to check out what is the value of R pi that we have obtained. 1 second. R pi was 2.4k. okay, so R pi is 2.4k. is the problem? Yeah, 2.4k. So let's just first solve 20 and 15. What do they come out to be? So they'll come out to be 20 times 15 over 35, which comes out to be 8.57 k parallel with 2.4k. So this will come out to be divided by It's plus 2.4, and it comes out to be 1.875k. So this parallel combination comes out to 1.875k, which is close to option A, 1.9. Okay, so option A will be our correct answer over it, and yes, it's option A in the answer key as well. So that's how we solve this problem. As always, if you draw the equivalent circuit diagram, right, things become very simple from then. And since we are required to find the input resistance, so in this case, that is the Thevenin resistance for this block, right? And we drew this block, and then again we saw there's no VBE over here, right? So if there's no VBE, then this part goes out, and anyways this is independent. So the only thing that remains is R1 parallel R2 parallel R pi, and we wrote the expression, plug in the values which are given of R1 and R2 and R pi, and we arrive at this answer of 1.9k. Yeah, so that completes our first set of problems. So 10 problems were required, and that was a very comprehensive how should I say this, very comprehensive coverage of the DC as well as the AC analysis of BJT. First we find the quiescent point, then we find when does it go into the active mode, when does it go into the saturation mode, when does it go into the cutoff, and then we also saw the small signal parameters like GM, R pi, and then based on GM and R pi based on GM and R pi, we then draw the small signal equivalent, from which we found out the small signal gain, midband gain, V0 upon Vs, if you recall. And finally we also evaluated the input and output resistances. All of them were based exclusively on the small signal model. There we were using this hybrid pi model. This is called the hybrid, looks like a pi. So this is called the hybrid pi model. Okay, so there's one so there's one error that I've been making, sorry about that. So I should clarify this. So this symbol that I've been drawing, so this symbol is for independent current source. Okay, while for voltage dependent current source, this is the symbol. This is voltage dependent current source. So just keep into this mind. So I was telling you that this is independent, hence this cannot be deactivated, but the symbol was wrong. Okay, so this is a diamond instead of circle. This is a diamond bracket outside this the arrow, which denotes the current source. Okay, which is the correct symbol is this, as you can see here. So apologies for that. Just please keep into the mind that this has to be a diamond. Okay, moving on. So now what we can so there are two models that we can use for solving the BJT problems. First is the hybrid pi model. We just saw it, that we found out input impedance, output impedance, and the gain. Second model is the T model. So depending on what the utility is, you can interchange them, interchange the two models. Like we saw in Thevenin and Norton equivalent, right? Similar kind of approach over here. So depending on our utility, we'll switch between them. Okay, so in this problem it says that the T model is an alternative small signal model of a BJT and is shown in the figure along with hybrid pi model, as you can see here. The parameters hybrid pi model of a specific BJT operating under specific bias conditions. So it's clearly mentioned there is some bias. I told you DC bias is important. So it's talking about the DC bias. So whatever the DC bias is, and actually this is what we had obtained in the last, if you remember, when RL was also 2K. So we had obtained RC equal to RL 2K. This is what we had obtained. Right, so that's not important. Let's drop this. Specific bias means we are talking about DC bias. What is alpha? Question asks, what is alpha? So this is the diagram that is given to us. Okay, so if you recall, then first what we'll do is that, if I remember, then R pi was beta over GM. Yeah, correct. From this we can get beta, that is the current gain, right, which will be GM times R pi. GM is 50 millimho times R pi, which is 2K. K and milli gets cancelled, so beta is a nice value of 100. What is beta? Beta is nothing but IC upon IB, so that is given to be 100. This is the first expression. Second, what we require is alpha. alpha is nothing but, if I recall, alpha is IC over IE. Okay, so I can write this as IC over IC plus IB. Okay, because by KCL, and thus I can write this as 1 over 1 plus IB upon IC. I'm dividing by IC, numerator and denominator both. Okay, this will come out to be 1 plus, now IB upon IC I know already from here, it's 1 upon 100, right? IC upon IB is 100, IB upon IC is 1 upon 100. This will come out to be 1.01. Okay, so 1 over 1.01 should be 0.99. Yeah, 0.99, coming out to be 0.99, very close to 1. And remember earlier I just very boldly I assumed that if beta is let's say 80 or 100 or 120, I simply said IC equal to IE, rather IC equal to IE, right? Or IE equal to IC, because alpha is very close to 1 in that case. So from that is the reason by which we can say IC equal to I. Mathematically now you can see in terms of alpha, right? So now we obtain the value of alpha, so that's that. So alpha comes out to be 0.99, which happens to be option C. Okay, so now the second part of the problem asks in the T model what is RE. So this is the T model that we have. So we already have, if you recall, alpha, what is alpha was 0.99. Okay, so we already have alpha, we need to find what is the value of RE. Okay, now how do you find RE? Now you can clearly see that if we apply Ohm's law across RE, if you apply Ohm's law across RE, you will get VB minus VE equal to this voltage minus this voltage. VB minus VE should be equal to IE times RE, right? From this we can get RE equal to VBE over IE. So this is the expression for RE that we have obtained now, but that is of limited use to us because we don't know VBE, right? And we also don't happen to know IE. Okay, these two are still unknown to us, but what we can do is that since, okay, just a second, so GM times VBE is known. Okay, got it. So what we'll do is that from hybrid pi model, I can say IC equal to, what is the value of IC? GM times VBE. Okay, now you got the value of IC in terms of VBE. So let's and we also know that this alpha is nothing but IC upon IE. Okay, so I can write this IC as 0.99 times IE equal to GM times VBE. This will give me IE equal to GM VBE over 0.9, and let's put this value over here. Okay, so this will give us RE equal to VBE, numerator remains the same, the value of IE is nothing but GM VBE. 0.99 is here, VB gets cancelled, we get 0.99 over GM. Okay, we get 0.99 over GM. So RE is 0.99 over GM. So 0.99 over 50, was it? Yeah, 50 millimole. So that will come out to be, this will become K, and that will be 0.99 by 50, which is 0.0198. Okay, so it's better to keep it in ohms. So it's shift the 3 decimals, it will be 19.8 ohms. Yeah, that's the correct answer. So option A, 19.8 ohms. So let me just populate the values over here. So R pi was 2K. GM was 50 millimole. RE we obtained, let's say 20 ohms approximately. Alpha we obtained as 0.99. So these are the two equivalent models that we have seen, and in these sets of problems where we were given RPi and GM, and we had obtained RE and alpha. So you can see that if you know, because essentially they belong, if the bias conditions are the same, they're essentially referring to the same BJT operating at the same bias conditions. Hence the models will be equivalent, and hence just because alpha and beta are interchangeable, we can find whatever we are comfortable with. For in this case we have GM, here we have alpha, but one register is there, RPi and RE. So based on your convenience or the requirement, we can change the models that we want to use. The answer naturally will not differ. Okay, so that's the main takeaway from these two questions. Their interchangeability from one to another, and that the applicability will depend on in the model, the way you are putting the model. Okay, just keep that in mind. All right, we still have around 34 minutes, which should be fine. Okay, so this question says the push-pull amplifier configuration is shown in the figure. So this is a push-pull amplifier. Why this weird name push-pull? Because what's going to happen is that so the hint, it says that note that only one of the transistors can conduct. So at any given point of time, only one of these transistors will be conducting. Okay, so for instance, when the V input is positive, okay, when the V input is positive, so you can see that there will be some VB, that there'll be some drop, but there'll be some positive VB that will be over here, right? And thus that would make sure that this Q1 transistor will turn on, and so Q1 will start to conduct. Okay, and so Q1 will start to conduct, and what will happen is that this node voltage will become very close to 5 volts. Okay, and that would mean that this node, the output, this is the output node over here, V out. This would mean is that the output node has been pulled up to 5 volts. Okay, in the other half, when let's say Vi is negative, minus 2 volts, minus 3 volts, this will be turned off, right? Because then this will become VBE will become sorry, in this case it's VEB. So VEB will become greater than, so this is the emitter here, right? We are taking the output from the emitter. Earlier in the previous problems, if you recall, we were taking output from the collector. Usually the RL was connected over here, right? But this time it's connected over here. Okay, so for the negative cycle, we'll see that this BJT will conduct, the top will be shut off, because it will be cut off, right? We saw this condition of cut off, that VBE, if it's less than 0.7 volts, this is the condition for cutoff, right? So keep that in mind. And so now let's jump in and solve the problem. So the transistor beta values are given for us, and with VI equal to 2 volts, what is I1? So let's see this problem. And so what we are given, these are the values that are given. Let me also just say this, that this is V out, because I might have some problems otherwise. Okay, so now let's just talk about when Vi is 2 volts. As I told you, Vi is 2 volts. We'll assume that only Q1 is conducting. Okay, and then we'll try to evaluate that what is the value of V0, and if our assumption is even correct or not. Okay, so let's just assume that V1 is conducting, and then so what we'll say is that assume Q1 in, yeah, Aditya? Somebody raised a hand, I think. Okay, sorry.
ओके सर, ओके, समझ गए सर.
Okay, thank you. So so we'll assume Q1 to be inactive, right? We'll see, we don't know whether it's inactive or not, but it's on. Okay, and Q2 cut off. Okay, so we'll see these assumptions, but let's just for now assume that, and we'll draw the circuit diagram. So how will the circuit diagram look like? This is Vi, this is RB. Okay, 5 volts, this is V0, and this is your current I2, this is your current I1. If you recall, we had solved these kinds of problems in last class, in the previous session, where we were talking about biasing of BJT. So this is a fairly straightforward in that aspect. Okay, so let's just go ahead and solve it. So what we do, first of all, let's just label some node. So we only need to label this node VB. Okay, and this is also VE, by the way. Okay, so what I'll do is that how should we proceed? Okay, so let's apply KVL. Let me do the different color. So we'll apply, so let's say, so this was the first step. Okay, and this is the second step. So we'll say KVL along purple line. So if we do that, I can write VI minus I1 times RB, which is the drop here, minus VBE, which will be the drop here, minus I2 times RL. This should be equal to 0. Okay, we know VI, we know VBE, because we are assuming it in active or saturation, whatever it is. This will be 0.7. Okay, so let's do that. So what I'll do is, this will be VI is 2 volts minus 0.7 equal to I1 times RB plus I2 times RL. Do we know the value of RL? Yeah, we know the value of RL. Okay, so this evaluates to, and okay, so now kindly note that I2 is nothing but IE, right? This is the emitter, the whole current is flowing through here, and we'll assume it approximately to be equal to IC, because beta is fairly large, 150. Okay, and I1 will be nothing but your base current. Okay, and we got to find the value of I1, so I can simply say, because beta is, so what I'll see, what I mean to say is this: since we know IC equal to beta IB, the value of IC is nothing but I2, beta IB is nothing but I1. So I2 equal to beta I1, and we'll use this value over here. Okay, this will come out to be 1.3. I'm using this information over here. I1 times 5k plus the value of I2 is nothing but beta I1 times 2k. Okay, let's now go to the next slide. This will be 1.3 equal to, I'll take I1 common, this will come out to be 5k plus beta times 2k. This will give me I1 equal to 1.3 over 5k, beta is what, 150, that will be 300, so this will come out to be 305k. This will give me I1 is equal to, let's calculate this number, 1.3 over 305, that comes out to be 4.26 milli over k, that will be microamps. So the expression for I1 that I have obtained is 4.26 microamps, which happens to be option D. Okay, that's fine, we evaluated, that's nothing, there's nothing special happening. Sorry, we just we assumed it to be active, Q1 is active, Q2 is cut off, and we evaluated that, and we found the value of this current, the base current, right? But now let's evaluate whether this is indeed inactive and Q2 is indeed in cutoff, because that is the assumption that we had, right? So how to evaluate that? So for that, this is the VB and this is VE, right? So we need to find the values of VB and VE, and then only we can confidently say that yes, indeed this was in active or saturation and this was in cutoff. Okay, so the value of VB we can clearly see is, the value of VB is simply VI minus IB times RB. Okay, so VI is nothing but 2 volts minus I1 is 4.26 micro, that is 5k. So let me evaluate this expression. This will come out to be 0 to 1, so that's 2 minus this is, that's coming out to be 1.98 volts. So this node voltage is coming out to be 1.98 volts. Okay, and and this VE, okay, VE is nothing but I2 times RL, which is nothing but beta I1 times RL. So let's calculate that. That would be 150 times I1, which is 4.26 micro, times RL, which is 2K. Okay, so this will come out to be 4.26 micro times 2 times 0.15. To convert it to that, this is coming out to be 1.28 volts. The value of V is coming out to 1.28 volts, and you can see VB minus VE is 0.7, and for NPN VBE should be 0.7, while for PNP VEB should be 0.7. So we are satisfying this condition but not this condition. So this clearly means that what we had assumed, that this is turned off and this is turned on, so that assumption is indeed correct. So that was not the incorrect assumption. That's what I mean to say about this. Okay, so it's a good practice just to verify the assumptions that you had made, right? That completes, that's a good check to perform. Okay, we can also see actually what's the value of VCE. So VC here is 5 volts, right? And 5 volts, and VB is around 2 volts, right? So VC, this is N, so N is at higher bias. So remember NPN, right? So N terminal is at higher bias as compared to P, so this is again reverse biased. So and VCE, as we see, is 5 minus 1.28, that will be 3 point something. So this Q1 is indeed in active mode. So that's what we had confirmed from just after obtaining the values. What we have done is that so yeah, that's the analysis part that we have done. So for now, so this is the same problem with VI is 2 volts. VI is 2 volts, and so remember we had obtained I1 equal to 4.26 microamps, right? And we simply said that, so I'll draw the circuit diagram for simplicity, for clarity, sorry. This is RB, 5 volts, RL, so this is I2, and this was our I1, this was our V input. Okay, so what we saw that that I1 and I2 is nothing but beta times I1, right? Because emitter current and this is the base current, and actually this is collector current, but since it's large enough, beta plus 1 can be approximated to beta. This will be 150 times 4.26 microamps, and this will come out to be 4.26 times 150, 0.64 milliamps. So 14 is coming out to be 0.64 milliamps. Yes, this is the option that we have. So here in this problem there's nothing much to do, because we had already done the hard work in the previous problem itself. The key thing here is that just to identify that which one is active, which one is cut off. So I think if you do that, then there's no problem at all. We'll be fine with that. Okay, so that's this thing. Now, okay, wait, what's going on? Okay, now we move on to the second set of the problems. In this case, now what we have done is that the topology or the configuration of this remains the same, except now Vi is negative. So when the input you're providing is a negative input, minus 2.5 volts. So now we can see that now what it's going to happen is that, remember this was at some higher potential, VE, this was coming out to be, if you recall, was it minus 1.28 volts, right? So now suddenly you have reduced this to be minus 2.5. Okay, now you can see this is no more forward bias. This is minus 2.5, this is minus 1.28. So this will enter cutoff. However, when this enters cutoff, what's going to happen over here? So this voltage will approximately be equal to minus 2.5, not exactly, but approximately minus 2.5. This is also approximately minus 2.5. Now you can see what's going to happen is that VEB over here, right? VEB will be greater than 0.7 volts for PNP. For this, you can see minus 2 point, V is minus 1.28 minus 2.5. So what will happen is that this transistor will turn on, this transistor will become active, this will become, I told you why this will become cut off, because emitter is at a emitter is at a lower potential, sorry, as at a higher potential as compared to the, this was plus 1 2.28 as compared to the base. Okay, so this will get turned off while Q2 will become active. So we'll write this down over here. So we'll see that Q2 will become active while Q1 enters cutoff. So when that happens, let's draw the circuit diagram. Okay, so this is VI, this is RB, this is current is I1, and now we know only Q2 will turn on, so we only need to consider that part. So this is minus 5 volts, this is RL, this is grounded. Okay, and this current that's flowing over here is I2. Okay, and this current is I1. The you'll see that the directions are going to reverse soon, right? Because we know the current will flow into the emitter. That's what this direction denotes for PNP, right? So we'll see, we'll quickly see that the value of I2 and I1 will come out to be they'll have a negative sign. So let's do that now. For step 2, what I'll do is let me choose a different color again. So let's apply KVL along this line. Mind you, this is emitter, this is VE, this is your base VB. So we'll say apply KVL along purple line. Let's do that. We'll write VI minus I1 RB minus VBE. That's how we are moving, right? And then again minus I2 RL. This should be equal to 0. Okay, now let's put in the values which we do know at least. So it will be I1 RB plus I2 RL. This will be equal to VI. The value of VI is minus 2.5 plus VBE. The value of VBE is nothing but minus VEB. Okay, and this will come out to be minus 2.5 minus 0.7. Remember, VEB is 0.7 volts. This is a PNP. Hence, not VBE but VEB. This is minus 3.2. You can clearly see that, you can see a negative sign. This means I1 and I2 both are inverted. Right. So one more assumption is that since this is nothing but IB, right? I'll write this here or somewhere. Okay, I'll write this here. So IB is nothing but I1 and IC will be nothing but beta I1, right? And IC I can also write it as IE, approximating. Okay, so let's do that. So we'll replace these values over there in the previous that we had. So I can so I'll write I1 RB, that term remains the same, plus I2 RL. So I2 is nothing but your emitter current, that's coming out to be beta I1. Beta I1 times RL, this was minus 3.2. Okay, so let's take I1 common. This comes out to be minus 3.2. This is from the beta expression. I have written that. So now coming to this expression, I1 would be minus 3.2 over RB plus beta RL. This will be minus 3.2. RB is 5K. Beta in this case, beta was different. It's beta is 80. Okay, let it go. So 80 times RL, which is 2K. This will be minus 3.2 over 5K plus 160, that will be 165K. This will again be in microamps. So 3.2 divided by 165 0.019. This is coming out to be 0.19, so 19 microamps with a negative sign. Okay, why is there a discrepancy in the answer? Let me just check. Did we do it correctly or not? Just hold on a minute. Let's do the analysis once again. So we saw that Q2 will become active and Q1 enters cutoff. That's fine. So this is the current I1 that is flowing. This is the base. This is the emitter that we have over here. Correct. This is the collector. Okay. So if I follow this line, this is VI minus I1 RB minus VBE minus I2 RL. This should be equal to 0. I rearrange I1 RB plus I2 RL. This should be equal to, okay, this is the error. So this should be minus VI. So minus of minus 2.5. Where? Go where? Which slide? Can you point? You can speak if you want. No, this is fine actually. Sorry about this. This is fine. So this will be VI minus VBE. VI minus VBE, that means VI. So that's the problem. It's VI minus VE. VI minus VBE. So that comes out to be, yeah, this will be a plus sign here. Okay, that was the error. It's coming out to be minus 1.8. Sorry about that. So let's do the hard work now. This is 3.2. This will get out. This will get out. This term will also go. What was it? Minus 1.8. Okay. This is minus 1.8, minus 1.8, minus 1.8. This is minus 1.8 over 165k. 1.8 over 165k comes out to be 10.91. Okay, 10.91 microamps with a negative sign. As I already told you, negative sign denotes the direction is, as it's noted here, it's the opposite of that, which makes sense. And so first let's talk about the answer. It will be option D. And now let's talk about the significance of this negative sign that you see here. This means opposite direction. Why is it opposite? It makes sense because in this cycle, when BI is negative, Q2 is in active mode, right? And Q1 is cut off. That's what we saw. So if it's in active mode, this means the current will be flowing in this direction actually, right? And here and here. And there is no current flowing through here. Okay. So what's going to happen? This VI is I1 value will naturally be negative because current is coming in this direction, and I2 will also be accordingly negative. Okay. So we saw that, and the expression, the value that we have gotten is minus 11 microamps. All right. Just a second. Okay, now moving on. So we had obtained, so now we are required to find the value of I2. So we know that I1 came out to be minus 11 microamps, right? And we know that I2 is nothing but beta times, let me say it like this. We know I1 is minus 11 microamps. That's from previous problem. Secondly, we know I can approximate it to be same as IC, right? Which is nothing but beta IB, right? And what's the circuit diagram that we're working with here? This is the circuit diagram. This is VI, this is I1, and this is coming through like this. This is minus 5 volts at collector. This is the emitter. This is RL of 2k, and this is the I2 that we are talking about. Okay, so I2 is nothing but so IE is nothing but IC, but beta IB. Now what's the value of IB? So this is the IB is flowing in this direction, so IB is nothing but so we can say IB is nothing but minus I1. Okay, so this will come out to be minus beta I1, the expression for IE. And also you can see so IE is actually in this direction, so this implies I2, which is nothing but minus IE, it's come out to be minus of minus beta I1, which comes out to be beta I1, which makes sense. Essentially just two negative signs get cancelled, so I2 is nothing but beta I1. Okay, so beta we know is 80, the value of I1 is minus 11 microamps. This comes out to be 11 times 8 is 88, 880 microamps. Do we have an option like this? D. So remember 880 microamps, you can write it 0.88 milliamps. Option is 0.87, but again that happens because we have assumed I equal to IC, and there are a few other assumptions. This actually was 10.9 or something. That's fine. We have got a close enough answer. So this is the option D that we have obtained. Now again, remember that what we had talked for problem 15 and 16, that this should be in cutoff and this should be inactive. Let's verify that now. Okay, so for that we need to identify these voltages, VB and this voltage VE. Okay, so let's try to find those voltages. So VB will be nothing but VI minus I1 times RB. VI is minus 2.5, I1 is minus 11 microamps, RB is 5K. This will turn out to be minus 2.5 plus 55 milli. Okay, so minus 2.5 plus 55 milli, so that's 55 milli is 55 by 1000, and we have to add minus 2.5 to that, so that comes out to be minus 2.45. let's say I'm rounding it off, minus 2.45 volts. So this node is at minus 2.45. let's calculate VE. VE is nothing but this, right? So VE is nothing but VE minus so VE minus 0 over RL, so that will come out to be nothing but I2 times RL. Okay, I2 we had obtained, minus 0.87 milli times RL, which is 2K. So this will come out to be 0.87 times 2 is 1.74. 1.74 minus 1.74 volts. Okay, so this node comes out to be minus 1.74 volts. And now if we obtain VBE, that is VB minus VE, comes out to be minus 2.45 minus 1.74, which is approximately minus 0.7 volts. So VB is minus 0.7 volts, which this means this will have to be cut off. Okay, so this would mean Q1 cut off, and this will also mean that VEB equal to 0.7, which would mean Q2 conducting, Q2 on, which we saw Q2 was on. And you can also see the VCE, right? Sorry, VCB, you can see VCE sat is greater than is minus 0.2, but this is around 3.2 value. So this is Q2 is on and Q2 is indeed in active mode. So this is an important check, and you should make, I advise you to make it a good practice about this, that whatever assumptions that you have had, right, just verify them after you solve the problem. It's good for it's a good practice for a subjective type of question, but it's even a good practice when you encounter objective questions or MCQs or some competitive exams that you might take. So it's just a good practice, it's just a good habit to have. Okay, so that's, I think this is the last question. That was the last question. So that is all. That's it for me. I'll be around because we still have what, 5 minutes. So in case you have any doubts regarding this session specifically, let's take that. And if not regarding this session, then some previous sessions or some other question that you are facing a problem, we can discuss that. So the stage is open. Feel free to ask. Aditya,
Yes, sir.
any doubts?
No.
Chalo, very good.
Thank you, sir.
Thank you for your time. Thank you. Good night.
Good night, sir.